interaction with environment. The context of this paper is automotive seat designs. Automotive seats are designed to reach some performance levels in domains as different as safety, comfort, durability. To study those domains, this industry is introducing more and more computer-aided engineering for economic reasons, which we will see. Regarding ergonomics, a lot of tools exist to compute static postures, but the analysis of motion is not so often handled virtually. To improve this, the DHERGO project was created. DHERGO stands for Digital Humans for Ergonomic Design of Products. This is a European collaborative project which involves academic and research centers, software editors, and car manufacturers. The goal of this project is to offer a solution for the analysis of motion to evaluate the design of products in terms of ergonomics. One of the innovations of this project is the simulation of accurate human-seat interaction in order to compute a more realistic motion. Another innovation is the use of human models with advanced musculoskeletal modeling to evaluate discomfort, the discomfort generated by the motion based on the articulation and the muscle stiffness, the muscle activity. Sorry. To do this, this solution requires an inverse kinematic engine for the prediction of the motion, a human model fully articulated to follow the predicted motion, with a deformable flash to compute the human-seat interaction, with a muscle network, and it needs to be adjustable in dimensions to match the chosen anthropometries. This solution also needs a finite element code to compute the interactions, and a muscular solver to compute the muscular activity necessary to perform the motion. So I will present here the components which were developed by ESI in the frame of this project. But first of all, I will describe a little bit the context of this project, which is the automotive seat design. So automotive seat, the first step of seat design is to locate where the occupant should be placed. The seat is usually defined after the car, so the location of the equipment, like the steering wheel or the pedal, is one of the constraints. The anthropometry can be chosen depending on the population targets, and another constraint is the range of motion for the different articulation. Using those, the ergonomic software will compute possible postures to reach the equipment, like the steering wheel or the pedal, to reach those equipment as comfortably as possible. For each of those possible postures, the center of the hip, called H-point, is extracted, and an average of all the possible H-point is defined and will be the seat reference point. So at this step, it is up to the seat designers and engineers to build an actual seat, which will, for which the occupant will have his H-point at the seat reference point. So to do this, they follow a process of trial and error loop. They will build the first prototype. They will test it to see if the H-point is at the seat reference point. If not, they will build a second prototype, test it again, and they will do this for different domains like safety, comfort, durability. So usually this process is done on physical prototypes, but the problem is physical prototypes are expensive and they take a lot of time to be built. So as such, this process does not leave any space for the necessary innovation to face the next challenges of seat design, like using recyclable light materials. So a solution is to use virtual prototypes, which are much faster to be built and easily modified. So, however, as I've said before, the seats have to be tested for different domains, safety, comfort, ergonomics, and so on. So the problem is, today virtual prototypes are used a lot for safety testing, but if other domains are not tested virtually as well, only the cost of physical prototypes for safety will be saved. So the best is to test virtually as many domains as possible. A software solution dedicated to seat design is currently being developed to enable virtual manufacturing and testing of all performances domains, so as to avoid completely at some steps the need and cost of physical prototypes. So the DHRGO project will extend this solution to ergonomic aspects, enabling and will enable engineers to evaluate the seat regarding comfort of motion using the kinematics and muscular activity. Now, concerning the DHRGO solution, one of the components developed by ESI is the human model. As I said before, this human needs to be fully articulated to follow the predicted motion. It needs to have a deformable flesh to measure an accurate interaction with the seat. It needs a muscular network to check out the muscular activation to perform the motion. And it should be adjustable in dimensions, shape, and physical capacity to match the chosen anthropometries. The PAM comfort model were chosen as base because they fulfill the two first requirements. Those models were based using a 2003 measurement campaigns in USA and Korea. The 5th, 50th, and 95th percentiles were defined for those populations. Candidates with close anthropometries were scanned. The resulting scans were used to build a finite element model. This model was defined as fully articulated with nonlinear joints, ligaments to model the spine flexibility. The organ motion was modeled, the lumbar pre-strain, and the stiffness in the torso muscle. The flesh was modeled also as deformable, with a distinction between the fat and muscle layer. So as I said before, this model needs to be used to provide a realistic contact interaction between the human flesh and the seat. So in order to have a good contact prediction, the volunteers were tested to get reference pressure maps. So here are the backrest and the cushion pressure. The exact same test was simulated with the same posture, the same anthropometries. The flesh was calibrated to get the right results, to be predictive. Now, concerning the other two requirements, the muscular network was implemented based on cadaver measurements. As for the scaling, a tool has been developed to adapt the models based on anatomical landmarks and external measurements. So with those four characteristics, the models are ready to be used in the DHRGO solution. Another component developed by ESI in the frame of this project is the muscular activity solver. This solver is used to compute the activation necessary in each muscle in order to balance all the external forces and also maintain the posture. External forces can be of any kind, local loadings like the support reaction forces, acceleration fields like the gravity, or inertial forces. This model, this muscular model uses a muscular model based on the Hill model. This Hill model decomposes decomposes the muscle action into an active component, the voluntary contraction of the muscle, and a passive component, the muscular tissue reaction to the elongation. Using this model, the solver will build equations to compute the necessary activation level, but the number of equations is dependent on the number of degrees of freedom in the model. So the problem is the number of muscle for which the activation has to be computed is much more important than the number of degrees of freedom. So in the end, there are more variables and constraints. And the problem is hypostatic. There are an infinite number of solutions. To compute the activation, the solver will minimize a function, either the muscle of force or the muscle of stress, or something else. So now that I've presented the components we've been working on, I will explain how they work in the global solution. So first of all, using a given anthropometry, an initial posture and a target, the inverse kinematic engine will compute the motion necessary to go from the initial posture to the target. This motion takes into account the obstacles and a simple interaction with the environment. For example, if the model, the human is seated, the pelvis will just be fixed. So the inverse kinematic engine will provide a motion file. The finite element code will read this file. It will impose to the human model the same anthropometry as the one used by the inverse kinematic engine. It will read the motion file and convert this into kinematic constraints with a freedom margin to let the human model adapt to the interaction with its environment. The finite element code will provide at the end an updated motion and the exact distribution of the external forces. Finally, the Muscular solver will analyze selected timeframes and compute the muscular activity necessary to balance all external forces. So now that I've described how this solution works, I'm going to present two examples. This first example is an application, is an illustration of the Diochergo application. So in this example, the human is seated with his left foot on the clutch pedal. The motion simulated is him pushing and releasing the clutch. The finite element code has computed an updated motion, which we can see here, taking into account the interaction with the seat. That's what we can see. It then provides the resulting pressure map to the Muscular solver, so it is used to calculate the activation level with more precision. We can see here the muscle activation in the main muscles responsible for the knee extension. Now if we look at the pressure map, when the leg is fully extended, we can see the changes in the pressure map can be directly related to changes in the activation level. Now the next example, it was made to simply illustrate the sensitivity of the muscle activation computation. So the motion simulated is going from crouching to standing. We can see first the muscular force in the knee extension muscle without the gravity. Then with the gravity, it's much more important. Then at a low velocity and at high velocity. Then again, we can see differences. So finally, to conclude, this solution enables to compute a more realistic motion using the interaction between the human and its environment. In the frame of this project, we have been able to develop musculoskeletal human models, which allows computing with the human-environment interaction the muscle activation necessary to perform the motion. The next steps of the project will be the implementation of the muscular network for the upper limb and torso, the creation of demonstrators for other motions, and the development of discomfort criteria. Thank you very much.
Do we have questions?
I was curious, I'm sorry if I missed this, but the coupling between the three-dimensional musculature and the line of action of the 1D musculature, how is that handled?
You mean how is the muscle model?
Well, the three-dimensionality of the muscle that you have to get, contact forces, and how is that handled in terms of its connection to the 1D musculature? Are there just offsets there? Are there three-dimensional geometry that's unpictured in some of these?
Actually, I'm sorry, I don't know the answers actually. I didn't work on that part of the project, so.
This is with bar elements, right?
Yes, it's with bar elements. And
This is only with bar elements.
Yeah, bar elements. They're attached to the bones. And after that, the interaction with the flesh, I don't know how exactly this is handled.
So probably some type of an offset condition between the flesh surface and these
There is
bar elements.
something, but I don't know exactly what it is. Yeah.
Is PEM component in the implicit or explicit software?
It's explicit for the time being, but we're trying to go to implicit also.
What typical runtime do you get, and how much is your actual runtime? I mean, the
For this kind
event,
of-
event duration and then the computer runtime.
For this kind of simulation? I don't know. I haven't, yeah, sorry. I haven't run them, so. I think it's hours, a few hours. So, not in minutes, mostly hours. But after that, I in details.
Okay.
When you're showing contact pressure on the seat, do you have anything that shows contact pressure on the tissues or the muscles or?
We do, there's no, I don't have animations, but we do take into account the pressure of the flesh, the deformability of the flesh, yes. But there's, I don't have any examples to show you. Yeah?
When you have this type of model doesn't have a backrest, that's correct, isn't it?
Yes, it does have a backrest, but we don't have the muscles for the back yet.
Okay, so is the model leaning against the backrest?
Oh yeah, in this simulation, yes, we have the whole, actually this simulation was done using a real life subject which did this operation, and he was leaning on the backrest. So
Yeah, but is the model leaning on the backrest?
yes, also, yeah. It's just that we've focused our animation on the legs, because
Yeah,
that's
but
where we have the
what I
muscle.
really want to know is so when you lean against the backrest, it means that the backrest is pushing against you.
Yes, there's a
And
contact
that
there.
creates shear forces between the buttocks and the seats. So are they included in the analysis? Because I think they are very important contributors to discomfort.
In this particular case, I don't know if they're taken into account, but they can be taken into account. I mean, the pressures of the whole seat can be taken into account. It's modeled after that. I don't know if in this particular case it was taken into account to compute the muscle activation, but it's doable, definitely.
Another question?